So today, this lesson, we're going to finish up chapter 5. This is section 5.5. In this section, we're going to be doing normal approximations for binomial distributions. So what we've learned kind of is the bell-shaped curve, especially using the calculator, we can get those probabilities rather easily. So our goal is, instead of using a binomial distribution, we're going to kind of more try to use the normal approximation instead. So this can happen in this situation here. So a normal approximation can be used in place of a binomial distribution if these are true. So the first one says if n times p is greater than or equal to 5 and n times q is greater than or equal to 5, then we can use a normal distribution in place of the binomial distribution. So again, we know that the mean is going to be n times p, and the standard deviation is going to be the square root of n times p times q. So remember, n is the number of independent trials, and p was the probability of successes in a single trial, and q is the probability of failure in a single trial. So if we go look up here, the number of trials times the probability of successes, that's got to be greater than or equal to 5 for us to be able to use a normal distribution. If our data does not meet that criteria, then we're stuck with the binomial distribution. So one of the things that has to be done is there's what's called this continuity correction. A binomial distribution is discrete. So again, discrete means it's countable. And we use a histogram for that. So to calculate exact binomial probabilities, you can use the binomial formula. Of course, we also have the calculator there that we kind of bypass some of that formula. So what they're saying here is you can use a continuity correction by using this 0.5. So I will either need to move 0.5 to the left and to the right of the midpoint to include all possible values of x in the interval. So this is what's kind of going to be going on here as we do this. So let's look at this example here. It says use a continuity correction to convert each binomial probability to a normal distribution probability. So the probability of getting 270, between 270 and 310 successes inclusive. Inclusive kind of means include the 270 and the 310. So basically what the binomial probability will look like then is this. It's going to be the probability of 270 is less than or equal to x, which is less than or equal to 310. So when you have a between statement, you actually read from the inside out. So I actually should read this as x is greater than or equal to 270 and x is less than or equal to 310. So it's in between those two values. So again, the binomial distribution would be like the histogram, the rectangles. Our goal is create what we call the normal approximation, which is going to be the bell-shaped curve. This means we get to use those z-scores and things like that. But again, we have our shortcuts in our calculator, so we don't have to actually do all that either. So if I should just, instead of doing all that, let's just try to model it on a simple number line. So if I have 270 over here, and I have 310 over here, inclusive means we're including these in the interval. So to make it continuous, we're going to have to shade in between 270 and 310. As a histogram, it's actually 270, 271, 272, so forth and so on. But by using this continuity correction, we create just an interval where there's no breaks, it's all smooth. So to include the 270, what I have to do is I have to move 0.5 to the left. So in other words, I would have to subtract 0.5 from 270. So 270 take away 0.5, that's going to give me this 269.5. So we want to be at this spot. And then notice now the 270 is included. And to include the 310, we actually have to go to the right of the 210 by 0.5. So in other words, I have to add 310, I have to add the 0.5 to that. So 310 plus then this 0.5 would give me 310.5. So what happens is we now have this interval here that we're going to use. This is going to be the normal distribution. And again, I'm not going to include the curve. So since it said include the 270 and the 310, they have to be part of the interval. So I have to move to the outsides of those intervals, of those two numbers. So now my normal will be then the probability of 269.5 is less than x, which is less than 310.5. So that would be my one that I could actually use and use the calculator on to find the actual probability under the curve, if you will. So next example, if we want to look at it, the probability of getting at least 158 successes. So the probability of getting at least 158 successes, that means you have to include the 158, but at least means you have to be to the right of it. So what your probability would be then is x is greater than or equal to this 158. So at least would imply that statement. So again, it's probably easier if we model this on our number line instead of trying to do all this others. So to try to create this normal probability, what I'm going to do is put the 158 on the number line. And at least means you have to be 158 or larger. So that's what we want. Now, to do the normal, since we're including the 158, we have to go to the left of 158 by 0.5 units to create the continuity correction. So actually, you would have to subtract the 0.5 from the 158, and that would give me then this 157.5. So our continuity correction means now we're going to use this interval, since it's now going to be continuous, no breaks. And so again, to include it, you have to have the 158's got to be part of the interval, so I have to move out to the left. Again, notice how greater than the symbol, notice how it points to where the shading is, and then equal to means you have to include the endpoint. So now if we use our normal, we're going to have probability. Again, we're going to have this x is going to be that now just greater than this 157.5. And that will now enable us to use a shortcut to find the probability using our calculator. So one more of these, we have the probability of getting fewer than 63 successes. Fewer than 63 successes means that we're not going to be including the 63. So it's going to be the probability of x is going to be less than 63. So fewer than means do not include. So if I was trying to model this on my number line, the 63 would go out here. And again, less than means, fewer than means to the left. Notice how my arrow is pointing to the left. That's a less than symbol. So here, we're not including the 63. To not include the 63, I don't want to move to the right, because if I move to the right, that's going to include the 63. You actually got to move to the left 0.5 to exclude that out of the interval. So we have to move over to this spot. So that means I have to go 63 take away 0.5, which would be then 62.5. So we're going to be using 62.5 in my normal. So it's actually going to be here to there. So my normal is going to be the probability of x is less than 62.5, since we're not including the 63 in our answer, in our probability. So this is a kind of a table that you can kind of use as well. So the left side's got the binomials, and then this tells us how to write the normal. So this is also something we can use as a reference. So use the continuity correction to convert each binomial probability to a normal distribution probability. So the probability of getting between 57 and 83 successes inclusive. So between, I don't really see that one up here as our examples. So, excuse me. So let me see here. Again, if you want, you can kind of make a number line as a kind of a guide to help you think it through. So right now, the 57 is over here, and the 83 is over here. Inclusive means to include the endpoints. So we use a solid dot there to say we include. And then we would be in between those values. So that's going to be our binomial. So the binomial probability would look like that. I think that's a little bit too many O's and stuff there. So it's going to be the probability of 57 is less than or equal to x, which is less than or equal to 83. So notice how, again, you would read it from the inside. You know, x is greater than or equal to 57. That's true. And x is less than or equal to 83. That's also true. So you're in between there. So to do the probability, since it says inclusive, this interval has to remain in the problem. So for that to happen, you have to move left of the 57.5, left of 57 by 0.5. So I have to use 57 minus 0.5, and that would give me 56.5. And here, to keep the 83 part of the interval, you'd have to move to the right of the 83 by 0.5. So that's going to be 83 plus then this 0.5. And that's going to give me 83.5. So I'm going to be using that interval for my normal distribution, because it now does include the 57 and the 83 as well. So my normal probability would be then the probability, again, your left bound would be that 56.5 is less than x, which is less than, and your right bound is going to be that 83.5. So that would be my normal distribution that I would use in my calculator. So the next example we have is the probability of getting at most 54 successes. So again, notice that at most is up here, and notice how we do include, at most does mean include the endpoint. So that's the catch, is do we include the endpoint or do we not include the endpoint? At most means we actually would include the endpoint. So that helps us trying to build this, this normal interval. So if I use my number line over here, the 54 would be here. At most means you can't go past 54, which means you have to be to the left. So as far as my binomial goes, that's going to be the probability of x is going to be less than or equal to 54 would be your binomial probability. What I want to do, though, is include this interval in my normal, and to include this in my normal, you actually have to go to the right of the 54 to include the 54. So you have to actually add a 0.5 to the 54. So 54 plus 0.5 will get us to 54.5. So that's going to become our normal probability that we can use. So that transforms into x is going to now be less than 54.5. And that would be how we would actually determine that probability. Okay. So we'll stop there.